All right, shall we begin? Okay, so something bad happened. I forgot the microphone attachment for my laptop. So the YouTube feed is going to rely upon the ambient sound of the room. That's going to be problematic. So say hello, YouTube. Hi, everybody. So if you're watching this live, I apologize for the sound quality. It's because I forgot the right attachment. So let's turn the screen towards the thing. You can see. Oh, look at that. Okay, so fun things today. A lot of deep analyses today. And what we're going to cover today are some things you're going to see again in your research methods class and again in epidemiology. So they're pretty important. Let's begin with this. This is actually the doctor's report from when my cousin took his newborn baby girl to the doctor. And if you look carefully, what they do is they measure her, they give her her height and her weight, and they show percentile measurements as compared to general population. Look, she's in the 101st percentile of height. How is that possible? Right. So my cousin's a statistician too. How did they figure that out? It's unclear how you got 101st percentile. Do you have any ideas? Sorry?
Taller than the average.
Taller than the average.
Oh.
Well.
I'm tired.
It's the beginning of the day. Is she taller than the universe? This is what it's kind of suggesting. Well, the obvious answer is that there's a standard reference population and she's taller than everybody else in the reference population, which is strange because she's tiny. But it's not physically possible to be 101st percentile. It's a mathematical anomaly caused by the methodology used that I don't fully understand. So this poor doctor just plugged in some numbers, she got a number, she reported it back. So when you get these kind of things, like squint at and think, well, that's not possible. But, okay, so today we're moving on to bivariate analyses. And bivariate means two variables. Anytime we have an association between two variables, we're doing bivariate analyses. And this is different from univariate and multivariate. So univariate analyses would be like taking the mean age in the room. I've got one variable, your age, and I'm doing something to it. A multivariate analysis would be figuring out what are the factors that are associated with passing this class. How much it has to do with your gender, how much has to do with your age, how much has to do with your previous experience, and so forth. Bivariate is just looking at the association between two variables. For example, are the men more likely to be older than the women? Right? Are the people who pass the class more likely to be left-handed than people who don't pass the class? Anytime we have two associating with two variables, it's a bivariate analysis. And really, for most people, that's what you end up doing in your statistics life. If you don't go on to do any sort of more complicated research, most of what we do is bivariate because it's easily understandable. And most of the stuff you'll read about in basic papers will be bivariate. T-tests or chi-squares usually involve bivariate analyses. So if you can really figure out how these work, then you're probably okay. What we're going to cover today are a special kind of bivariate analyses, which are measurements of association, typically used in population health research. And I'm pretty sure this is going to be new to everybody, but they're pretty important. This is the foundation for most population health research. So here's some examples of height and weight. The one we're going to spend a lot of time on is looking at things like exposure, which is smoking status, and an outcome, like lung cancer rates, and so forth. Now, as always, the kind of statistical approach we take depends on the level of measurement, nominal versus ordinal versus continuous. The ones we're looking at today are pretty much nominal. They're pretty much binary outcomes. Before we get there, one of the common things we do in bivariate analysis is cross-tabulation. You've probably seen this in SPSS already. If you click on analysis and crosstabs as one of the options. So cross-tabulation is looking at the frequency distributions of different options in your variables. For example, gender versus smoking, yes or no. So we have gender over here, male, female, smoking, yes, no over there, and we just distribute which one's which. How many are smokers are men, how many smokers women, how many are non-smokers men, how many non-smokers women, so forth. So the most common kind of contingency table that we use for cross-tabulation is a 2x2 table. And here's what it looks like. So here again is male, female, smoker, non-smoker. I could go on. I could make a 3x2, a 4x4, a 10x10 table. I can have male, female, other, smoker, non-smoker, ever smoker, never smoker, maybe wants to smoke. Right? So I can have endless numbers of categories. We like the 2x2 table because it lends itself well to some easy computations. The things we're doing today are all using 2x2 tables. Now the book calls these cross-tab tables because we are cross-tabulating them. In epidemiology, we call them contingency tables because the outcome is contingent upon an exposure. Whether or not you got cancer is contingent upon whether or not you smoked. So I would tend to use those terms interchangeably. Technically, cross-tabs are any time we cross-tabulate something. A contingency is any time there's an exposure and outcome. So those are technical distinctions. The textbook only uses cross-tab, so don't be confused when I slip and call them contingency tables. Notice that when we present a cross-tab or contingency table, we sometimes have totals as well, these shaded areas here. So we call the sums at the ends of these rows and columns marginals. So the marginal total for smokers is 10 men plus 10 women, 20. The marginal total for women is 40 non-smokers and 10 smokers, 50, so forth. So the marginal will come into play later on when we look at how to compute agreement and chi-squares. So the marginals allow us to figure out how much are expected in each of these groups. Because if everything was random, there'd be a relatively even distribution of characteristics across the bunch here. And we can figure out what a random distribution is by looking at the marginals. Right? So the extent to which our actual distribution differs from an expected random distribution is really the essence of looking for an effect or significance. If it's not what we expected in terms of randomness, probably something going on. Right. So here are the shaded parts are the key component to the table. Notice there are 2 rows and 2 columns. It's a 2x2 table. If I were to show you this table and ask you what kind of table is this, someone's going to tell me it's a 3x3 because they see 3 rows and 3 columns. No, it's a 2x2 because the data is only in 2 columns and 2 rows. The marginals don't count as data. Right, still with me? Excellent. So how to read the crosstab table. And experts get this confused all the time, so don't be concerned if you get straight application. I remember my first job after my PhD, I was reading crosstab tables wrong. I was writing these reports entirely incorrectly. I wasn't paying attention, so don't be ashamed if you get it wrong a few times. So here in a row, for example, for the same data, looking just at the men for a second, we see that the first one is the number of people in the cell. The second is the percentage distribution across the row. The third is the percentage distribution across the column. What does that mean? 50% are male, 20% are smokers. So 20 plus 80 is going to be 100, and 50 plus 50 is going to be 100. And 10% is the 10% of all of the sample. So go back here again. It's probably clearer. Notice these two add up to 100, and these two, 20 and 80, add up to 100. And these all add up to 100. So get that clear in your mind. Right? So if I ask you what percentage of smokers are female, what's the answer? What percentage of smokers are female? Whisper. Yes, that's right. 50% of smokers. So all the smokers add to 100. The distribution of smokers is that. If I ask you what percentage of the men are non-smokers, what's the answer? 80%. Exactly down here. Okay, so that's how we read that part. Okay, so now that we're clear on how the cross-tabulation depiction works, the kinds of measurements of association we're going to go through now. So we often say smoking is associated with lung cancer. We say in lay language smoking causes lung cancer, but we actually don't know for sure. We don't know with scientific precision and certainty that it does, having to do with the inability to do a certain kind of experiments on it. But we do know that smoking is strongly associated with lung cancer to the point where it's pretty much guaranteed that smoking causes lung cancer. But what do we mean when we say associated? We mean something very specific. We mean that according to a series of measurements of association, the indices we compute suggest a strong amount of association. The three indices we're going to explore today are relative risk, odds ratio, and distributable risk. Have we heard these terms before? Yeah, we've heard it. Oh, elaborate. Okay, so getting ahead of the curve. Right, good. So this will all be reviewed then. Excellent. But we're going to go over it more thoroughly today. So these are actually the key measurements that you find in most public health documentation today. We look at often what is the relative risk of getting this if you live under a power line, or the risk of having a good job if you're well educated. You compute these things whenever we can. So I said all that. Right. So before I describe how to compute these things, we need to go over the kinds of study designs that result in the data. Have you learned about cohort and case control studies before? Anyone learned about it before? Good, this is on you. You're going to go over this again in your research methods class and again in epidemiology. So there are a variety of ways of organizing an observational study. The first kind is what we call a case control study, and it looks like this. We begin with the people who have a disease we care about, and we have some people who don't have the disease we care about, and we look back in time to see whether or not they were exposed to the thing we care about. So in the example of smoking, well, back here, example of smoking and lung cancer, our cases are people with lung cancer. You find them in the hospital. We find some people who don't have lung cancer, probably in the same hospital because we want them to be as similar as possible. And we go through their medical records, or we ask them, did you smoke in the last 10 years, and if so, how much? And we compute how many of them smoked, how many of them didn't, how many of them smoked, how many didn't. We compare these two proportions to determine if the proportion who smoked amongst the lung disease people is different from the proportion smoked amongst the non-lung disease people. Okay. So this is a step-by-step method of how to do it. Step one, you ascertain the people who have the disease, you ascertain people who don't have disease, and you look backwards in time to see whether that's called a case control type study. Again, we're going to do this ad nauseum in research methods. I bring it up now because the kind of measurement of association you use kind of depends on where the data came from. The other important observational study design is the cohort design, and this is more intuitive. This is the opposite of the case control. In the cohort design, we begin by ascertaining the exposure status. So we have a bunch of people, the city of Ottawa. We find some people who smoke, we find some people who don't smoke, and we wait and see how many get cancer, how many don't get cancer, how many get cancer, how many don't get cancer. We compare this proportion to that proportion to see which is larger. So if the proportion who get cancer in this group is bigger than the proportion who get cancer in this group, what can I conclude about the association between the exposure and cancer? Is there an association? Yeah, something like that? Yeah, there probably is. The question is, what size of difference matters to me? Or if this group is smaller than that group, then there's an association in the other direction. And sometimes it's true. So if my outcome is Parkinson's, if my exposure was smoking, non-smoking, and this is Parkinson's disease, no Parkinson's, no Parkinson's, I'd actually find a higher amount of Parkinson's in the no smoking group than the smoking group, because smoking is actually protective against Parkinson's, believe it or not. We don't have to talk about that. But every exposure causes things and is protective against things as well. So that's the standard cohort design. This is more intuitive, as opposed to the case control design, which is not particularly intuitive. We use this a lot for outbreak investigation. So if you go to a picnic and a bunch of people got diarrhea from the picnic food, we find it's easy to show up after it's already happened and we have some people who have diarrhea, people who don't have diarrhea from the same picnic, and ask them, did you eat the tuna salad or didn't you? Did you eat the tuna salad or didn't you? They figure out, if you ate the tuna salad, did you have a higher chance of getting diarrhea? That's how we figure out if, in fact, there's an association between the tuna salad and getting diarrhea. Isn't it great starting your day with a diarrhea lecture? There we go. Okay. So, the book calls these terms prospective and retrospective. It's not entirely correct, right? So a prospective design is a cohort design. A retrospective design isn't always a case control design. But we'll go what the book says. For the purposes of being consistent in the class, and so you have a reference to go to all the time. The book is always correct, even though in this case they're not entirely. There is such a thing called a retrospective cohort. That's when we start with the exposure and wait until the outcome, but it happened in the past. Go through medical records to see how it happened in the past. That's a retrospective cohort. But the key distinguishing characteristic between the two is that the first one, the cohort, begins with ascertaining the exposure and waiting to see if the outcome manifests. The case control begins with ascertaining the outcome and looking backwards in time to see if the exposure was present. That's the key difference. If it helps, this is moving forward in time, this is moving backwards in time. Okay. Then we have experiments. What I just described are observational studies. An experiment is different from an observational study because in an experiment, you, the researcher, manipulate a variable. You do something to change it. Right? So in the previous examples, nobody told them to smoke. They smoked on their own. Right? So when I found some lung cancer people, I didn't give them lung cancer. I just found them, and I found some people without lung cancer, and I measured if they smoked or not. Or I found some smokers, I found some other smokers, and I waited to see if they got lung cancer. In an experiment, I'd make you smoke it. Right? A lot of people, you're smoking, you're not smoking. I'd make sure you do that. Obviously, we can't do that. So an experiment is all about the researcher having control. So there's, oh, that was a good one. Fine, I'll just put this brain. That's an experiment. You do something and something happens. It's a joke. So here is the classic experiment, the randomized control trial, or the clinical trial. Again, I'm moving fast through this because it's not that important for this class. I just want you to be aware of it, and we'll go much more in depth in the research methods and epidemiology classes. So a clinical trial looks like this. We have a population, and we randomize into two groups. Right? So let's say I'm testing out a new migraine alleviation drug, and you're my population of people who say, hey, we're migraine sufferers. So for you, I'll flip a coin and say, hey, heads, you're going to be in this group, and you're tails, you're in that group, and so forth. So randomly select which one goes in this group. And this group, I'm going to give you my new drug, and this group, I'll give you something else, probably a placebo, which is nothing, or some other drug. And then I compare the two to see which ones have fewer migraines. And that becomes my outcome measure. The distinguishing characteristic between this and a cohort is that I tell you which drug to take. In a cohort, you take them naturally. And that's what to see what happens. So the randomized clinical trial is the gold standard for evidence in our Western society. That's why we don't really believe this causes that unless this and that have been through a randomized control trial scenario. Very expensive process. This is what drug companies do all the time. This is where all the money in epidemiology is, if you're interested. Okay, so another example. Here's an experiment. What is the better study method for the midterm, reviewing slides or studying the textbook? So people in this class, I'd randomize you into two groups. One group with all look at the slides, the other group with the textbook only, and I'd see which group does better at the end of the exam. Okay, pretty straightforward stuff. So those are the designs. Now we're going to figure out, once I have my data from this experiment and from the observational studies, how do I determine if there's a difference? Let's say I didn't tell you about odds ratios and relative risks, and this was the design. How would you determine or measure if there's a difference in outcome? I can leave it up to you to figure out a way. We know who's in which group, and we know what marks they got at the end of the midterm. I gave you all that data, yes?
You could use like the measures of central tendency and then just compare.
Oh, you're getting fancy. So what does that mean?
Just like look at the mean and median and then.
Okay, so the mean mark in this group versus the mean mark in that group. Sure, that's fair enough. Yeah, That's one thing we could do. In fact, that's something some people do. I said do. Okay, so, but that's not what we're going to do. Do something else. So here's a summary of scenarios. Cohort, we follow your people forward. Case control, we follow them backwards. And randomized control trial, that's a classical experiment. All right, so by the way, the word cohort comes from the Roman legions. They were divided into cohorts, and they always move forward. That's what we call them, cohorts. I just said all this before, and why I'm saying it again. Cohort study begins with exposure. There it is. I'll skip you the example because I'm just going over the same thing before. All right. So I'll give the example again for case control because that's sometimes it's the hardest one to understand. So the example here is do ARV drugs are they associated with nausea? An ARV drug is an antiretroviral drug given to AIDS patients often. So in the study design for a case control analysis, we'd find some people who are nauseous and some non-nauseous people and check to see if any of them took antiretrovirals. As an aside, if I did this experiment, if I went out into downtown Ottawa, are you nauseous? Are you nauseous? Right? And I asked a bunch of people, then I asked them, did you take ARVs? What are the chances I would get some who took ARVs? Probably pretty small, right? So this is not an appropriate design type for this particular research question. Because the number of people who take antiretroviral drugs is so small in our community that if I just went out and found some nauseous people, you probably were drinking last night. You probably got the flu, I don't know. Whereas the case control, well, the cohort example works better. How would I do the same question using a cohort design? The exposure is the drugs, and the outcome is nausea. Yes? Exactly. So I find some people who took the drugs, find some people who didn't take the drugs, and I find out which ones become nauseous. And that's easy to do. I just go to an AIDS clinic and find some people on the drugs. Right. The smoking example I've given you already. So here's another example. This is 6 people with Creutzfeldt-Jakob disease. What's Creutzfeldt-Jakob? Never heard of that disease before. It's mad cow disease for humans. That's what it is. So very rare, one of the rarest diseases in the world. So we have 6 people with Creutzfeldt-Jakob disease and 10 without. And we'll look back to see how many were exposed to Subway Santa Fe chicken sandwich. Okay, so that is what? What kind of design is that? The giveaway is I look back to see. Yes, is that case control? Absolutely. Right. Now, if I've done this same experiment using a cohort method, how would it look? Yes. Yeah, so I give some people a sandwich, I give some people no sandwich, and I wait to see who develops Creutzfeldt-Jakob disease. And will anybody develop it? No. Maybe at any given time, 10 people in the world have Creutzfeldt-Jakob disease. Chances are I'm not going to detect any of them. So the kind of design I apply depends on the nature of the disease and its frequency and so forth. All right, so those are the design types. Now we're going to look at how we assess risk or association. Right, so the kinds of risks we're going to look at are absolute risk and relative risk. So an absolute risk is, well, as it says here, the actual quantity of risk. How much, if I do this, how much more likely is it I'm going to get the disease, and if I don't do this? Whereas relative risk compares the risk in 2 different groups. So here's the thing. If I tell you, if you smoke, your risk of getting cancer is this. That's pretty scary. But the real question is, how much more risk is that than if I don't smoke? Because even if you don't smoke, you have a risk of getting cancer. That's kind of the kicker with relative measures, is understanding that even if you don't do all the good things we tell you to do, you still have a chance of getting the bad thing. Right? So what we're interested in is the excess risk, or the additional risk, or how much greater risk is there. So beware with these absolute measures. It doesn't really tell us a whole lot more than, it doesn't tell us how much above baseline your risk is associated. Right? So let's look at it. This is a contingency table for our data. Again, this is a cross-tab contingency table. The way we set it up, and it's important to set it this way, otherwise the formulas don't work, is we have our outcome are the columns, and our exposures are the rows, and the yes and the no must come first. The yes must come first in each case. If it's reversed, the math doesn't work. I think the textbook may have made a mistake in one of the examples. Look for it carefully. They may have reversed the table. I might be confusing textbooks here. The EPI textbook, I don't make a mistake in one of them. So one of the first things to look at is make sure when you make your table, the yes is on top, the yes is first over here. So in this case, if it's smoking and lung cancer, this would be yes, I smoked, no, I didn't smoke. Yes, I have lung cancer, no, I don't have lung cancer. Can't reverse it. Now, is this a 2x2 table or a 3x3 table? It's a 2x2. Our red parts are my data, and the black parts are the marginals. And notice I've labeled these A, B, C, and D. Okay, so maintain that labeling convention, because this is the way the formulas are going to play out using this labeling convention. Okay. N is, what is N always? What does N mean again? Remember N? Sample size, right? So in this case, N is A plus B plus C plus D. N is everybody. All right, so here we go. Lung cancer, no lung cancer. So in a cohort design, we follow 100 smokers and 100 non-smokers over 10 years to see which group develops more lung cancer. Okay, and here is our data. Notice, even if you don't smoke, 10 of you got lung cancer. Right? That's important consideration, because this is why we're going to compute these measurements of relative risk. We want to know how much more the risk is if you smoke than if you don't smoke. Right? If I smoke, 75 of my sample got lung cancer. If I just looked at this group, which is what journalists and lay people tend to do, oh my God, I smoked, I got. I'll give you an example. I was at a dinner party once, a long time ago, and haven't been invited back since. And someone said to me, "Do you know that every single sex offender in jail looked at porn in his life?" And I said, "I bet they ate bread as well." I mean, what are you trying to say? And she's very mad at me. The point I was trying to make is, what matters is, did they look at porn more so than men who weren't sex offenders, right? Did they eat bread more so than men who aren't sex offenders, right? And that didn't get across with my sarcastic comments. So I've since learned to be a little more sensitive to people's rationality. Right. So we have a total of 200. Some got cancer and some didn't. Right. So put that example aside for a second and move on to another example, which is probably a little less intuitive. And this has to do with, I took this example directly from the textbook, so that's why I switched over. This is fictitious data for the effect of a shorter versus longer needle on swelling for pediatric immunizations. So in this case, we care about, do I want to switch over to a shorter needle when giving kids injections to produce less swelling? Right, so here's my data. In this case, the exposure is the smaller needle as opposed to the large needle, and my outcome is swelling versus no swelling. And I've got a total of 200 people. Here's my distribution. So amongst those who got the smaller needle, 20 got swelling and 80 didn't, and here the large needle, 10 got swelling and 90 didn't. So let's break it down. My absolute risk is the proportion of people who got the swelling. So over here, the absolute risk in my 60 millimeter group is 20 over 100. So 20% got swelling. That's the absolute risk of swelling in my exposure group. I call this my exposure group. This is my non-exposure group, because I wasn't exposed to the thing I care about. Now, I'm phrasing it very carefully, because how we set up our contingency table depends upon what we're trying to measure. Ask yourself always, what is the exposure we're trying to measure? In this example, the exposure is the effect of the smaller needle. So the absolute risk in my exposure group is 20%. The absolute risk in my non-exposure group, exposure, is 10%. Straightforward. Okay, 20%, 10%. Now, we have something called the absolute risk reduction. And this is the difference between the absolute risk in the exposure group and the absolute risk in the unexposed group. This is the risk in the small needle and the risk in my large needle, 20%, 10%. And the difference is 10%. So in other words, there's a 10 percentage point reduction in the risk of swelling in the longer needle. Okay, so in this case, the longer needle appears to be a better option because there's a lesser risk of swelling. Now let's look at the relative risk. The relative risk is the ratio between the two absolute risks. Get complicated, right? So we can compute our absolute risk in the exposed group and the absolute risk in the unexposed group, just divide them. So in this case, we have 20% and 10%, divide them. We get 2. So children immunized with a shorter needle were twice as likely to have swelling than the large needle. So in this example, there's a 10% reduction in swelling, so we know it's going in the right direction. That is equivalent to a twofold increase in swelling. Right? So with me, it's just a matter of plugging in numbers and computing them. So relative risk is really the gold standard in observational studies. You always want to measure relative risks. It's a quick and easy way to see if something's going on. We use it for every kind of exposure and outcome. Classically, smoking and lung cancer, like living near power lines, et cetera, et cetera, et cetera. We always want to go for relative risks. And the magic is that anytime you have a ratio, the magic number is 1. Anytime you're dividing two things of the same unit, the magic number is 1. So I have a ratio of 1. What does that mean? It means the risk in the first group relative to the second group is the same. No difference. So 1 means nothing's going on. There's no difference in risk. If I have something greater than 1, then there's positive risk. If it's less than 1, then there's negative risk or protectiveness. Right? So in the case of smoking and lung cancer, if the relative risk is greater than 1, I know that smoking is associated with lung cancer. In the case of Parkinson's disease, if this is like 0.5, I know that Parkinson's disease is protective. Again, so smoking is protective of Parkinson's disease. Right? The magic number is 1. Now the other question is, what's a good number? And that's a debatable qualitative thing. I would say that 2. Anything with a relative risk of 2 is probably important. 1.5 is probably important. Anything around there, less, we don't really care that much about, depending upon what it is. But if you read in the paper that this has a relative risk of 2, oh my God, pay attention. That's a big exposure. Here's an example. So we saw this data already. This is smoking and lung cancer. Right? Our 200 people who followed. My relative risk is the absolute risk in the exposed group, which is going to be what? Absolute risk in my exposed group is what? 75 over 100, so 75%. The absolute risk in my unexposed group is 10 over 100, right, or 10%, right, and or 7.5. That's a huge number, huge. That tells me that yes, smoking is much riskier than non-smoking when it comes to getting lung cancer. It doesn't mean if I don't smoke, I'm guaranteed not to get cancer. It just means if I do smoke, the risk of getting it increased by 7.5 times. Huge. Yep. Now we care about this other thing called relative risk reduction. A lot of terms to remember here. Relative risk reduction is my absolute risk reduction divided by the absolute risk in my non-exposed group. Okay, remember my absolute risk reduction is when I subtracted those two absolute risks. Right? So in the case of the needle example, that was 0.1. And my absolute risk in the unexposed group was the large needle, the proportion. I just divide those two. Okay, so what this tells me is how much the relative risk is reduced as a result of my exposure. All right, looking around blankly. You try the examples and then get back to me with confusion. Okay, so for the smoking example, you can plug in the numbers again and get this enormous number over here. So avoiding smoking reduced the relative risk of lung cancer by 650%, according to the data I just gave. That's how we use those magical numbers. Now, moving on to the last measurement of association that we're going to cover. Any questions about relative risk first? Good. Yeah. Yes.
Which one was more effective?
Effective? They tell different stories. Depends on the story we're trying to tell. You have to use the verbiage quite carefully. What we care most about is always the relative risk. That's the one everyone understands well. It's the one that drives most policy. This kind of thing, relative risk reduction, is useful, in Parliament bang on. You cut down smoking, you reduce your risk by 600%. It's a bigger number. It sounds impressive, but really, it's relative risk we care about. Okay. It's recorded, isn't it? It's not good. I'm on the record of making fun of parliamentarians. I'm worried about the audio here. I'm gonna speak up more. Okay, good. Odds. What are odds? As opposed to probability. Are they the same thing? Okay, if I have 100 students and 60 are female, what is the probability of being female in that class? Sorry. Whisper, 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 whisper. See here? Of 100 students, 60 are female. Therefore, the probability of being female is what? Whisper, 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 whisper. Commit. Show some courage. Commit. 60%. That's correct. Wasn't that hard, right? What is the probability of being male in that class, assuming you only have male and female options? 40, exactly. Now, the odds are different from probability. Odds is the ratio of probability to not probability. P over 1 minus P. In other words, the probability of being female divided by the probability of not being female. So 60 divided by 40. What's that? 3 over 2. 1.5. The odds 1.5. So it's, yeah, 1.5. Okay? So that's the difference between odds and probability. Why do we care about odds? A gambler or anything else. So the last measurement of association is comparing the odds of getting your outcome versus the odds of not getting your outcome. Sorry, I'll say that again. The odds of getting your outcome with the exposure compared to the odds of getting outcome when you haven't got your exposure. Okay? So the odds is a proportion of people in each risk group who have the adverse outcome relative to the proportion who do not. Example I just gave you. 80% of the class are female. The odds of being female is 80 over 1 minus 80 or 4 to 1. Okay. So here is our exposed group again. Imagine the consistency table is big like this. I've got my exposed, my outcome, my exposed, my marginals. The odds in the exposed group is A divided by B. The odds in the unexposed group is C divided by D. Very straightforward. Okay, straightforward stuff. The odds ratio now is going to be just dividing those two. So here again is my needle example. The odds of getting the swelling for my small needle is what? What numbers do I divide? The odds of getting swelling if I use a small needle. 20 over 80. Right. The odds of getting swelling with my big needle, 10 over 90. Exactly. Right. So 25 in the first one and 0.1 in the second one. Straightforward. Okay. The odds ratio is I divide those two and I get 2.25. So the odds are 2 1/4 more of getting swelling using a small needle than a big needle. Okay, straightforward, pretty good. There's a fast way of doing it. If you do the arithmetic, you find out that that big formula is the same as this divided by that, the cross products. A times D divided by B times C. Just like that. That's what we always do. Exactly the same number. Okay. So here is our same data from a smoking example. Remember that this data gave us a relative risk of 7.5. Here we use these cross products, these two divided by these two, and we get 27. So the odds ratio is 27 here. Right? Odds of lung cancer are 27 times higher if you smoke. So what's better, odds ratio or relative risk? Relative risk is better. We always like relative risk. But the thing is, you can't always compute a relative risk. The reason I showed you those study designs, case control and cohort design, is because how you got the data affects which kind of thing you can use. You can only use a relative risk with a cohort design and experiment. You can't use a relative risk with a case control. And the reason for that is because I'm selecting the case control, I'm selecting the outcomes. I find my lung cancer patients, and I find my people without lung cancer. I'm affecting my outcome numbers. I'm affecting my incidence rates. I'm affecting the risk. So it's artificial. Depending on who I select, I can get any number I want. So the relative risk has no meaning in a case control design. So we use an odds ratio to estimate the relative risk. Okay? So relative risk is better, we prefer it. An odds ratio is used to estimate a relative risk. We haven't got it. The thing is, I just showed you that in my smoking example, the odds ratio was very different than my relative risk. Right? Relative risk is 7.5, the odds ratio is 27. How can one be used to estimate the other if it's so different? The answer is that odds ratio is used to estimate relative risk when the disease is rare. What is rare? Depends, whatever. It's a qualitative judgment. Lung cancer is not rare, okay? But most other things are kind of rare, and rarity is defined as its prevalence in the community that we care about. Right? So I'll say it again. When the disease is rare-ish, odds ratio can be used to estimate the relative risk. The relative risk can never be computed from a case-controlled design. A lot of new stuff, right? Good. All right. Next thing we're going to measure is the number needed to treat. Whew, here's a new one. So this is, we care about this in drug development studies because we care about how many people we actually need to get the drug or the interventions before we have any sort of meaningful change in the population outcome. And the number needed to treat is defined as 1 divided by my absolute risk reduction. Remember, the absolute risk reduction was the difference between the absolute risk in my exposed group and the absolute risk in my unexposed group. I subtracted them. Now I'm going to divide that number into 1. So the example we had before with the needles was 10. So what does that mean? It means that 10 children would have to be immunized with the larger needle before we saw 1 case of swelling reduced. So hopefully you see the application of this computation. It's there are vaccination studies, right? So how many people need to be vaccinated before we prevent 1 case of the disease? Usually it's not up to 10, so that's much less than. All right, so that's how we compute the number needed to treat. Very straightforward. So here is the smoking example. My same data for smoking. So number needed to treat is 1 divided by the absolute risk reduction. Here are my numbers in absolute risk reduction. I get 0.65, I divide to 1, and I get 1.54. So I need to have 1.54 people not smoke for me to have 1 fewer case of lung cancer. Does 1.54 people have any meaning? I can't find 5.54 people. My sister is quite short, but she's still a full person. Yeah, just like a joke, less fun. So instead of 1.54, what's the actual number? How many people needed to treat? How many people need to stop smoking for me to have 1 fewer case of lung cancer? Is 1 enough? Is 2 enough? Yeah, obviously 2. 2 is the closest number of people I can get. That's not 1. Right? So we round up to the nearest person. Okay. And I mentioned relative risk is preferred to odds ratio because it's more intuitive, etc., etc. Right. I mentioned rarity. That's all. So that's your homework. That's a lot of stuff. I know. Everyone's so clear, right? No one's traumatized. Good. All right. So, whew. Yes, ma'am.
So that kind of rounding it up that way, because that kind of staying on the safe side.
It's not saying the safe side. I mean, if it's obviously 1 person is not enough. The number is 1.5, and so it must be 2. There's no such thing as 1.5. Simple as that. Okay. Yeah, exactly. It's 1.2 is still 2 people. That's right. You always go up. Yeah. Stop this.